Let's elucidate the quantum phase estimation algorithm by exploring this quantum circuit diagram and mathematically describing the quantum state at 4 key stages. The steps in this algorithm can be adapted to perform the order-finding subroutine of Shor's factoring algorithm. Let's define the phase that we are trying to estimate. The target of this quantum phase estimation algorithm is an L-qubit unitary operator denoted by capital U. This unitary operator has an eigenstate denoted by lambda with an associated eigenvalue that is expressed in the format of this complex exponential. Because this is a unitary operator, we can express the eigenvalue in this format. We have e to the 2 pi I phi, where phi is the phase. This phi over here is the phase that we are trying to estimate with this phase estimation algorithm. Let's have a look at the notation for the eigenstate and for the phase. So because this is a L-qubit eigenstate, we're putting an L in the superscript over here. So we're using Dirac notation, and we're putting a lambda inside of this ket. And this L tells us that we need L qubits to represent this eigenstate. An alternative way of expressing this is as a string of qubits. The label for each of these qubits is a bit. So lambda sub L minus 1, lambda sub L minus 2, all the way up to lambda sub 1 and lambda sub 0, these are bits. They can be either 0 or 1. And this 0 or 1 actually allows us to denote the computational basis states for a single qubit. So each one of these are single qubits, and we're going to initialize each of those single qubits as either a 0 state or a 1 state. And then we're going to have a string of these bits, which will be the label for this L-qubit eigenstate. And we can either write it in this condensed form or we can write it in this full form. And note that these are actually tensor products. We're taking the tensor products of qubit states. So we're combining these single qubit Hilbert spaces into an L-qubit Hilbert space. So this is actually the state that we're going to initialize one of the registers in this algorithm. So we have a register of L qubits, and we're going to initialize those L qubits in these initial states. And that's going to allow us to initialize the eigenstate of this unitary operator U, which is the target of phase estimation. Now, let's have a look at the phase. We need mu bits to define the phase. So we can express this phi as 0 point, then this string of bits. So over here, we're not dealing with decimal notation. Instead, we're dealing with binary notation. The subscript in each of these terms is associated with the power of 2 that multiplies these terms in a sum. So if you look at this summation notation over here, we can see a sum over some index j going from 1 to mu. And the terms in this sum have the format phi sub minus j times 2 to the minus j. So this first term over here, this is going to be multiplied by 2 to the minus 1. And the next term will be multiplied by 2 to the minus 2. And we'll keep going all the way up to the muth term. So this term over here is going to get multiplied by 2 to the minus mu. We can either write it in this summation notation, or we can write it as this string of bits after the point. So we have 0 point, and then we have a string of bits. And this string of bits is actually what we're going to be measuring at the end of this quantum algorithm. So that is what we're trying to measure. And this phase over here is enough information to determine the eigenvalue. So it's actually equivalent to determining the eigenvalue. We could also think of this as the eigenvalue estimation algorithm. But because we're dealing with a unitary operator, we can define this eigenvalue in terms of the phase if we express the eigenvalue in the format of this complex exponential, e to the 2 pi I phi. So we have seen this notation for the L-qubit eigenstate of the L-qubit unitary operator U, and we have also defined this notation for phi, and this is the phase that we are trying to estimate. It is important to note that mu is the number of bits that we need to express this value of phi. And we are considering a special case of the phase estimation algorithm. This is the exact case. So we have mu bits over here, and mu bits are enough to exactly express phi. So phi is a real number in the interval 0 to 1. It could be equal to 0. If phi is equal to 0, then this eigenvalue is equal to 1. But if it's not equal to 0, then it can go between 0 and 1. And we don't want to include the value of 1 as a possible value because of the cyclic nature of this complex exponential. If we put 1 over here, then we're going to have e to the 2 pi I. And e to the 2 pi I is actually the same as 1. So then we will have two different inputs over here, and they will give us the same eigenvalue. So we're going to restrict this to all real numbers in the interval from 0 to 1, including 0, but excluding 1. Those are the possible values for phi. And what we're going to do is we're going to restrict ourselves to a phi that can be expressed exactly in terms of mu bits. If we cannot express this exactly as mu bits, then we will have a mu bit approximation. So then it will be an estimation procedure. But first, in this video, we're going to explore the exact case, and we're going to build up an intuition of how phase estimation works. And then in later videos, we will explore the estimation part of this procedure. These are cases where we're not actually measuring the exact value of phi, but we're measuring a good approximation for that value of phi. Now that we have introduced some notation for this problem, and we've actually stated the problem, let's examine the quantum circuit diagram. Time flows from top to bottom in this diagram. Vertical black solid lines represent qubits. Each of the qubits are labeled at the top of this diagram. The qubits are organized into two registers. On the left, register X contains mu qubits. On the right, register Y contains L qubits. Note that we have these dots that keep appearing in this diagram. When you see three horizontal dots, they indicate that qubits have been omitted. In this diagram, we're only showing the first, second, second last, and last qubit in register X and in register Y. All of these intermediate qubits have been omitted. We want to keep this diagram very general. So this diagram is an accurate visualization for values of mu and L that are larger than 4. If we get rid of all of these dots, then we will have the visualization for the case where mu is equal to 4 and L is equal to 4. And if we want to deal with cases where we have mu and L equal to 1, 2, or 3, then we just have to remove some of the qubits in this diagram. But we want to deal with large values of mu and L. So mu and L are positive integers. And for practical applications of the quantum phase estimation algorithm, they're going to be large positive integers, much larger than 4. So that is why we're choosing to represent this diagram in a very general way, with the intermediate qubits being omitted. So we have enough information to illustrate the patterns that are present in this diagram. Let's have a look at the initial states at the beginning of the quantum phase estimation algorithm. What is going on in register X? All of the qubits in register X are initialized in the single qubit computational basis state labeled by 0. We could also represent this in a different way. We could represent this as a string of mu zeros. And we could put that string of mu zeros inside of a ket. So that would be the label of a ket. And that would be the collective quantum state of this entire register on the left. So that is the initial state of register X. So we're just initializing them in the state labeled by 0. But what is going on in register Y? It's a little more complicated. Let's have a look at the labels for these qubits. Here we have lambda sub L minus 1, lambda sub L minus 2, and then all the way down to lambda sub 1 and lambda sub 0. These are bits, so they can have a value of 0 or 1, and they serve as labels for each of these qubits. And these initial qubits, when we take the tensor product, they're going to give us the eigenstate lambda. So that is an L qubit eigenstate of the unitary operator U, which is the target of phase estimation. So that is that eigenstate that we introduced previously in this video. So we are initializing register Y in that eigenstate. That eigenstate lambda is the initial state of the register on the right. And the initial state of the register on the left is just all zeros. So that is what we're dealing with for the initialization part of this procedure. And if we have a look at this green line slices through the diagram right after initialization. So that green line is going to provide us with a snapshot of the quantum state after initialization. It is going to reveal the initial quantum state. Then, after that part of the procedure, we have these Hadamard gates, which are represented by a H in a box. So we have a Hadamard gate that's being applied to a single qubit over here. And we do that for all of the qubits in register X. So in total, we have mu Hadamard gates being applied to each of the qubits in register X. But note that there are no Hadamard gates being applied to the qubits in register Y. That's the same as applying the identity operator. So we're not changing the quantum state of register Y yet. Then when we get to this blue line, we have another snapshot of the quantum state. So that snapshot is going to show us a superposition that is being created by all of these Hadamard gates. So by applying all of these Hadamard gates to the qubits in register X, we're going to create a superposition of all of the computational basis states for register X. So these are mu qubit computational basis states. So that is what's going on in this blue stage. The next stage involves these controlled unitary operators. And this U over here, that is the same U that we defined previously. This U is the unitary operator that is the target of phase estimation. And we are raising that to powers over here. So we have U to the power of 2 to the 0, then U to the power of 2 to the 1. And we go all the way up to U to the power of 2 to the mu minus 2, and then U to the power of 2 to the mu minus 1. So we can see a pattern emerging over here. Even though the intermediate values over here for all of those powers are omitted, we can still see the pattern that is growing. So the exponents are powers of 2, and they start from 2 to the 0, and they go all the way up to 2 to the mu minus 1, much like the labels of each of these qubits. So furthest to the right, we have 0, and then as we progress to the left, we work our way up to mu minus 1. That's what's happening with the labels of all of these qubits in register X. What's happening with the labels of the qubits in register Y? Well, it's a similar pattern, but in place of mu, we have L, because register Y contains L qubits. So that is what's going on in these exponents over here. But what is this notation over here? We have a quantum gate. It is a special type of quantum gate. It is a controlled gate. So this solid black circle is placed on the control qubit. And then we have a horizontal line which links the control qubit to the target. And the target is, in this case, not just a single qubit. It is an entire register of qubits. So all L qubits in register Y are the target of this controlled unitary gate. And you can see that the first controlled unitary gate has this qubit x sub 0 as the control qubit. And then the pattern progresses. We move over to x sub 1, and then we skip over all of the intermediate gates, and then we get to the final 2, and we can see mu minus 2 as the subscript, and then mu minus 1 as the subscript. So these over here are the control qubits. That is what this solid black circle is denoting. And then that horizontal line is linking us over to where the target is. This is the target of this controlled unitary gate. So once we apply this sequence of controlled unitary gates, we're going to get to this red snapshot. So the red snapshot shows us what happens at the end of this sequence of controlled unitary gates. And if we examine the quantum state there, we will see some interesting features. Then finally, we have another quantum gate over here. So this is the last quantum gate that we're going to be using in this procedure before we perform measurements of all the qubits. This notation over here tells us that we're dealing with the inverse quantum Fourier transform for mu qubits. So F for Fourier transform, this subscript of 2 to the mu is telling us the Hilbert space, and mu is specifying the number of qubits. So if you have mu qubits, the Hilbert space associated with all those mu qubits, that's going to be 2 to the power of mu. And that is what's appearing in this subscript. And we also have a dagger, and this dagger is telling us that we're taking the Hermitian adjoint. And that's the same as the inverse. So we're dealing with the mu qubit inverse quantum Fourier transform. That is what this box over here denotes. So this is another quantum gate. But note that inside this box, we're going to have many other gates, including the Hadamard gate. So this Hadamard gate is going to appear many times in this quantum Fourier transform box. And we will actually unpack all of the details inside of this quantum Fourier transform in another video. After we perform the mu qubit inverse quantum Fourier transform on all of the qubits in register X, we're going to be ready to perform measurements. And just before we perform measurements, we have this purple line. And this purple line is giving us another snapshot of the quantum state. So we're going to have 4 snapshots in this procedure. The green line we can call initialization. The blue line we can call creating superposition. The red line we can call the application of all of these controlled unitary gates. And then this purple line we can call the state after performing the inverse quantum Fourier transform. So these are 4 key stages in this algorithm. And then at the very end of the algorithm, we're going to measure all of the qubits. And we're not actually interested in the results of the measurements of register Y. So register Y is actually not very important at this part of the procedure. But register X is very important, because when we measure each of these qubits, we're going to get bits. And bits are denoted by these double lines to distinguish them from the qubits, which are denoted by black solid lines. And these bits over here correspond to the mu bits that are needed to represent the value of phi. So remember, the whole goal of this algorithm is phase estimation. We're trying to estimate the value of phi. We're given a target unitary operator, which acts on L qubits. And we're also given an initial eigenstate, denoted by lambda. That's this initial state of register Y. And given those those pieces of information, the goal is to estimate the value of phi. And in this video, we're actually considering the exact case. So mu bits are sufficient to exactly express this value of phi. And we can measure these exactly, and we're going to see how we actually do that. We're going to see a justification as to why these are the results of the measurements of all of those mu qubits in register X. So we're going to have a look at the mathematical descriptions of the quantum state at each of these 4 key stages. And before we talk about this red state over here, we're going to need to introduce the quantum Fourier transform. And the quantum Fourier transform is going to help us see how we can go from this red snapshot to the purple snapshot. But first, let's have a look at initialization and creating superposition. Those are the green and the blue snapshots. This green snapshot shows us two alternative notations for the initial quantum state of all qubits in both registers. That includes all of the mu qubits in register X and all of the L qubits in register Y. This notation on the left explicitly shows all of the initial qubit states that are shown in the diagram. And on the right, we can see a condensed notation. Let's actually interpret what this notation is telling us. So on the left, we can explicitly see the first, second, second last, and last initial qubit state in both register X and register Y. The dots over here tell us that we have some qubits that are omitted, but we have enough information to illustrate the pattern. So all of the qubits in register X are initialized in the single qubit computational basis state labeled by 0. What this notation is actually telling us is that we have a tensor product of all of these mu qubits. And this tensor product is being used to combine all of these qubits together to give us a mu qubit state. So we could also write this as a ket with a 0 and then a tensor product, and then another ket with a 0 and then another tensor product. And we keep putting tensor products in between all of these kets. But that is a bit redundant because this notation communicates it very clearly. Another notation we could use is we could put a string of mu zeros inside of a single ket. And that string of mu zeros would communicate that we are initializing all of these qubits in the state 0. And that string of zeros is actually a binary representation of 0 using mu bits. So alternatively, instead of writing all of those mu zeros, we could just write a single 0 and we could put a mu in the superscript. That's where this condensed notation comes from. So when you see a 0 inside of a ket and there is a superscript mu, that is telling you that this 0 is not a single qubit state. This is a 0 for a mu qubit state. So we have mu qubits and they're all initialized in the state 0. So that's what's going on in register X. What is happening in register Y? In register Y, we have L qubits which are encoding the eigenstate lambda. So this is the eigenstate of the unitary operator U, which is the target of this quantum phase estimation algorithm. So all of these qubits over here, they are being used to encode the state denoted by lambda. And you can see a superscript L, and this superscript L is telling us that we need L qubits to actually encode this state lambda in individual qubits. So whenever you see this explicit notation, note that what we're doing is actually taking the tensor product of many single qubit states. And that's going to give us a collective state of all of those qubits in the register. So now we have the state of register X and the state of register Y. So register X is initialized in this 0 with a mu, and register Y is initialized in this lambda with an L up here. So that's telling us that we have mu qubits in register X and L qubits in register Y. So do not confuse this 0 for a single qubit state. It is not a single qubit state. It is the collective state of mu qubits. It's the quantum state of an entire register of qubits. So this notation is very useful. It's a condensed notation which avoids all of this long, tedious, explicit notation for all of the individual qubit states. Now let's move on to the blue snapshot. The blue snapshot shows us the quantum state after we apply the Hadamard gate to all of the qubits in register X. And register Y is left alone. So that's the same as applying the identity. We're not doing anything to the state of register Y. We're just applying a Hadamard gate to all of the qubits in register X. And we can denote that using this long form explicit notation. So we have a H and that H is acting on each of these single qubit computational basis states labeled by 0. So what is that going to do? That is actually going to create a superposition of all of the computational basis states for register X. So this is a very long form notation. Let's have a look at a more condensed notation. We can put H with a tensor product sign followed by mu. So the reason I'm putting a tensor product sign over here is so that we don't confuse this with exponentiation. We're not raising this unitary operator to an exponent. Instead, we are taking the tensor product of many h's together. In fact, we have mu h's. And if we take the tensor product, we're going to get this unitary operator which acts on a mu qubit system. So this is a Hadamard gate with a tensor product mu. And that's the condensed notation for all of this stuff over here. And you can see that the state is denoted using this condensed notation, where we have 0 and then a superscript mu. And the condensed notation for the state of register Y is still the same. We haven't done anything to register Y. It is still in that eigenstate of U. Another way of writing the state of register X is this notation over here. We have a normalization coefficient of 2 to the minus mu on 2. We have a normalization coefficient of 2 to the minus 1/2 that comes from applying each of the Hadamard gates. And because we have mu of those Hadamard gates, that explains why we have mu appearing in the exponent. So all of those normalization coefficients are getting multiplied together, and we can use exponential laws to combine them into a single factor. And when you apply the Hadamard gate to the state labeled by 0, that takes it to a superposition of 0 and 1, with the appropriate normalization factor of 2 to the minus 1/2, which can also be written as 1 over the square root of 2. So this superposition is the result of acting with the Hadamard gate on that initial state. But we don't just have a single qubit, we have a tensor product of all of the qubit states. So all of the qubit states have been put in this superposition. And if we take the tensor product, then what we're going to get is a uniform superposition of all of the computational basis states for register X. And we can also write that using this summation notation. So G over here is a label for all of the computational basis states. And we have a uniform superposition. So G is going to go from 0 up to 2 to the mu minus 1. So this over here can be thought of as decimal notation, but we can also write this in binary notation. We could write this G as a string of mu zeros. So just like what we were talking about up here, over here, we could write this as a string of mu zeros. Or we could alternatively write it as a single 0 in decimal, and we can just put a mu up here to tell us that we're dealing with a mu qubit system. So that is how we can also express this over here. So we can think of this as bit strings of length mu. So mu bits in a string, and we consider all of the possible combinations of zeros and ones. So each of those bits can be either 0 or 1. And that means because we have mu of them, we have 2 to the mu possibilities. So 2 to the mu computational basis states are present in this superposition. And we're starting from 0. That means we have to go up to 2 to the mu minus 1. So we don't go up to 2 to the mu because we are starting from 0. That's why we have to subtract 1 over here. And you can express that G in decimal or in binary. You could express it as a string of mu bits. And over here on the right, we still have lambda. That is our eigenstate of the unitary operator. Another point that I want to stress on before we move on to the quantum Fourier transform is that the Hadamard gate takes us from the eigenbasis of Pauli Z to the eigenbasis of Pauli X. So this 0 state over here, this is an eigenvector of the Pauli Z operator, and it has eigenvalue +1. And this state over here, this superposition of 0 and 1 with a normalization coefficient of 1 over the square root of 2, that is an eigenstate of the Pauli X operator with eigenvalue +1. So that's what the Hadamard gate does. It takes us from the Pauli Z eigenbasis to the Pauli X eigenbasis. So we have seen a snapshot of the initial state, and we've also seen a snapshot of the state after we create a superposition of all of the computational basis states in register X. And we're leaving register Y alone. We're not doing anything to register Y after it gets initialized in the eigenstate of the unitary operator U. Now we're ready to move on to the quantum Fourier transform. In the quantum circuit diagram for phase estimation, we saw that the mu qubit inverse quantum Fourier transform was applied to register X. This came after a sequence of controlled unitary gates. To understand the details of these steps in the quantum phase estimation algorithm, we need to define the quantum Fourier transform. F subscript 2 to the power of mu denotes the mu qubit quantum Fourier transform. So we're dealing with a register of mu qubits, and the dimension of the Hilbert space is 2 to the power of mu. We're putting the dimension of the Hilbert space in the subscript. So that is telling us which quantum Fourier transform we're dealing with. So what is the dimension of the Hilbert space? That is enough information to specify what kind of quantum Fourier transform we are applying. And F is for Fourier. So this is the notation for the mu qubit quantum Fourier transform. And it is being applied to this initial state. And this initial state is labeled by capital Phi. And you can see that this is actually the same type of condensed notation that we used previously, because there is a superscript mu. We could write this out in long form. And in long form, we have this string of bits over here. So phi sub -1, phi sub -2, ... phi sub 1 minus mu, and phi sub mu, these are the mu bits that are required to express phi. Because we're dealing with the exact case of quantum phase estimation, we only need mu bits to represent phi. And each of these values that are labels in these kets, they are bits. So they can either be 0 or 1. And the subscript tells us which power of 2 we have to multiply by. And these guys are going to show up in a sum. And that is how we're going to define phi. So the goal of quantum phase estimation is to estimate the phase. And because we're dealing with the exact case over here, we have the exact representation of the phase, which is given by these mu bits. So capital Phi is actually equal to this string of mu bits. And we are encoding this in the language of qubits. So that's why we have Dirac notation over here. Each of these bits are labels of a ket. And this over here is implicitly a tensor product. We're taking the tensor product of all of these single qubit states. And when we take the tensor product of all those single qubit states, we're going to get a mu qubit state. And we're showing the first, second, second last, and last one of these qubit states. All of those intermediate states are omitted, but we have enough information to illustrate the pattern. So this is a long form notation for the initial state, and over here we have a condensed notation. So every time you see a big phi, note that this is condensed notation for a string of mu bits. Now that we have seen this initial state notation, let's see what happens when we act with the quantum Fourier transform on this state. This over here is the tensor product notation for the quantum Fourier transform. So this is one way of defining the quantum Fourier transform. What we have is a normalization coefficient out the front, and then we have these superpositions of single qubit computational basis states with relative phase factors. So we have the state 0 and the state 1 in a superposition, and then this phase factor of e to the 2 pi I times 0.phi sub minus mu. What does this notation mean? Well, we're dealing with binary notation over here. We're not dealing with decimal notation. So this is actually telling us that we have phi sub minus mu times 2 to the minus 1. And 2 to the minus 1, that's the same as 0.5. So this is the 1/2 place. So we're not dealing with decimal notation. This is not the same as 0.1. This is actually 0.5 if we were to write this in decimal. And you can see that in this first term, we're just dealing with this final bit. But in the next term, we shift over and we have the final bit and the second last bit. And if we go all the way to the last two terms, we're going to have phi sub minus 2 all the way up to phi sub minus mu. And if we go to the very last term, we're going to have phi sub minus 1 all the way up to phi sub minus mu. And so this is the entire bit string. So here we have the entire bit string that is present in this phase, inside the phase factor. So this bit string over here, this is the same as big phi. But we have to multiply it by a power of 2 in order to shift it beyond this point. So you can see we have 0 point this entire bit string. That means we are multiplying this value of big phi, which is a bit string, by 2 to the minus mu. We want to shift it over mu places. And that is how we're actually achieving this. We're multiplying by a factor of 2 to the minus mu. And you can see that this second last term has a factor of 2 to the 1 minus mu. So we're not shifting all the way. We're not shifting mu places. We're shifting mu minus 1 places. And that's why this phi sub minus 1 term gets cut off. And if we go to these first two terms, we're only shifting by 2 places, and over here we're only shifting by 1 place. So we're only interested in these bits that appear after the point. Why is that the case? Well, it's because if we have an integer which is greater than 1 over here, then we're going to have an integer multiple of 2 pi in this complex exponential. And any integer multiple of 2 pi, that's going to take you around the unit circle in the complex plane. And so you're going to get back to exactly where you started. So it's that periodic nature of the complex exponential. So we're not interested in integer multiples of 2 pi, but we are interested in fractions. We're interested in fractional multiples. And all of these values that are after this point, after 0 point, and then we have this bit string, these guys represent a fraction. So the first bit in the string represents the term that multiplies 0.5 in decimal. So that would be a half. And then the next one is a quarter, and then an eighth. And we go all the way down to 2 to the minus mu. So these are the coefficients if we were going to write this out in summation notation. And we actually saw that in the definition of phi at the start of this video. So that is how we go from this definition over to this step over here. So you can see that this line where we have all of these bit strings after 0 point, and then we have that bit string, that binary notation, that's the same as this big phi notation, where we're just multiplying this big phi by a factor of 2 to the minus times some integer. And because we have a common pattern emerging over here, we can write this in this condensed notation with a big tensor product at the front. So we're taking the tensor product from j equals 1 to mu, and this index j is showing up over here. So we have a placeholder, that's this j, and j goes from 1 all the way to mu. And you can see that it is minus j in the exponent, because in this pattern we have minus 1, then minus 2, and then 1 minus mu, and then minus mu. So that's why we need a minus sign over here. So that's the pattern of this tensor product definition of the quantum Fourier transform. And note that we also have this normalization coefficient out the front. And it's the same normalization coefficient that we encountered previously. We have 2 to the minus mu on 2. Why is that mu there? Well, it's because we have mu qubits. And every time we are dealing with a single qubit and we create each of these superpositions of 0 and 1, we need a normalization coefficient of 2 to the minus 1/2. That's the same as 1 over the square root of 2. And so we need that normalization coefficient for each of those terms. And if we use exponential laws, we can group that together, and we're going to get a mu appearing in this exponent. And we can also write these two terms inside the brackets of this big tensor product as a sum. And we can sum over this index g. And this index g is going to have the subscript mu minus j. So the reason I'm choosing this notation for the subscript is because we can use the same format that we use to label the qubits in both registers. So the labeling system that we're using, we're going to have the same format for this subscript over here. So we have G with a subscript mu minus J. And that's going to take on two values inside of these brackets. It's going to be either 0 or 1. When this index is 0, we're going to get rid of this complex exponential, because we're just going to have e to the 2 pi I times 0, and that's equal to 1. So we'll just have a coefficient of 1. And this label for the state is going to be 0. So that explains the first term in the superposition. It's just the ket 0. And what about the other state? Well, that's when we set this index equal to 1. When it's equal to 1, then we have e to the 2 pi I, capital phi times 2 to the minus j. And what is the label for the state? Well, it is 1. So that's what we're dealing with inside of the ket. So this summation notation actually takes care of both of these terms inside the brackets. So now that we have this, what we can do is actually take the tensor product and then pull out all of those sums. So there's going to be a sum for each value of j going from 1 to mu. And that's going to give us all of these sums. So we're still going to have the normalization coefficient out the front, and then we're going to have all of these sums. And all of those sums are going to go from 0 to 1. So we have two options, 0, 1, 0, 1. All of those options are going to be there. And there are going to be j terms in this big sum mess out the front. And what's going to happen to the exponential factors? Well, we're going to have to multiply a complex exponential for each of the terms in this tensor product. And we can use exponential laws, and we can turn that multiplication into addition within the exponent. So that's where this sum inside of the exponent comes from. So we still have e to the 2 pi I, capital phi, and then we have this big sum. And inside the sum, I've multiplied by a factor of 2 to the power of mu. And that means I have to divide by 2 to the power of mu. That's the same as multiplying by 2 to the minus mu. So this 2 to the minus mu and 2 to the mu can cancel each other out. And that will just leave the same format that we had over here. We have g sub mu minus j, and then 2 to the power of minus j. And that is the same format that we had previously. But now we're dealing with this extra summation, because we have to multiply by an exponential factor for each of these terms in the tensor product. And what is going on with the quantum state? Well, the quantum states are all being tensor producted together. So first we're going to have g sub mu minus 1, then g sub mu minus 2, all the way up to g sub 1 and g sub 0. And we can think of this as a bit string. And that bit string of mu bits is going to define a positive integer mu. And we can write this big mess of sums and tensor products as a single sum. We're going to sum over a single index, g, and g is going to go from 0 up to 2 to the mu minus 1. We have seen this type of summation format previously when we applied all of those Hadamard gates to the register on the left, to register x. And we also had this kind of sum, and we had the same normalization coefficient. But now we have these complex exponential factors over here, and they are the coefficients of all of the states in this superposition. So what is the label for this state? Well, it is just g. And we have this superscript mu, and that is telling us that we're dealing with a mu qubit system. So this is condensed notation for this entire string of bits over here. So we could write this as a string of bits for all of these g's with subscripts. And another way to interpret this is a tensor product of qubit states. So if we take a tensor product of all of those qubit states, we have mu of them, we're going to get a single mu qubit state. And that is labeled by the index g. So g can be expressed in decimal format, as we are doing over here. We're expressing it as a single 0, and we're expressing it as 2 to the power of mu minus 1. We could also write this in binary. We could write it as strings of length mu. So all of those computational basis states going from 0 up to 2 to the mu minus 1, they can be written as strings of length mu. So 0 would be a string of mu zeros, and if we go all the way up to 2 to the mu minus 1, that would be a string of all ones. So we would just have all ones inside of this ket. But alternatively, we could just write it in decimal notation. So this format over here, where we have e to the 2 pi I, g times big phi, and then 2 to the minus mu, this is analogous to the discrete Fourier transform. So the discrete Fourier transform, that can be done on classical computers as well. So we have a format that is analogous to the discrete Fourier transform. And we have shown that it is equivalent to this tensor product definition. So we have these two different definitions for the quantum Fourier transform. One is very familiar. We have a discrete Fourier transform that is used in electrical engineering. But what is going on with this tensor product definition? Here we have something that is a little less familiar, but it will make more sense when we see the quantum circuit diagrams for the quantum Fourier transform in later videos. So we have these two different ways of expressing the quantum Fourier transform. We have this discrete Fourier transform analogous way, and then this more novel way that is kind of unique to quantum mechanics. And one last thing that I want to stress on is, where did this 2 to the minus mu factor come from? Well, this 2 to the minus mu factor at the very end actually came from multiplying and dividing. So in this definition over here, in this sum in the complex exponential, I had a factor of 2 to the mu minus j. So I specifically multiplied by a factor of 2 to the mu, and then multiplied by this 2 to the minus mu to cancel that out and make sure that everything is equivalent. And I chose to do that so that I could have the same format over here. So that the same subscript that is present in each of these g terms is the same term that multiplies them. So that's a convention in all of the notation in these videos. When you see a subscript for all of these bits in a bit string, that tells you the power of 2 that they get multiplied by. So that convention we're going to stick to. It's a consistent convention. And what we're going to do is we're going to use this final form of the quantum Fourier transform. So it's analogous to the discrete Fourier transform, and we're going to use that form, and we're going to see that it appears later in the next few snapshots. But it's going to be slightly different. Instead of having this capital phi times 2 to the minus mu, we're going to redefine that as a lowercase phi. And we will see that now. This red snapshot at the top tells us the quantum state after the sequence of controlled unitary gates are applied in the quantum phase estimation algorithm. Let's examine the notation for this quantum state. First, we have our familiar normalization coefficient, and then we have a collection of sums. Each of these sums are going over an index, and that index can take on values of 0 or 1. That means the index over here is a bit. All of these indices are actually bits. And pay particular attention to these indices. They show up in multiple places in this expression. So the indices are also the labels for each of the qubits in register X, and they're also showing up over here as exponents of this unitary operator. So let's first focus on the left side of this diagram. We have a superposition of all of the computational basis states for register X. How did we create that superposition? Well, we applied a Hadamard gate to each of the mu qubits in register X, and that produced a superposition. And we wrote that superposition as a sum over an index g, and g went from 0 up to 2 to the power of mu minus 1. So g was just a single index, and it went through all of the values, and all of those values were a label for one of the computational basis states for this mu qubit system. And that mu qubit system is register X. We are choosing to express this in an alternative way. Instead of having a single index g, we are expressing g as a mu length bit string. So we have mu bits in a string, and we're using each of those strings to express one of the computational basis states. So that's why we have so many sums over here. We have mu sums in total. And that is a very elaborate way of expressing that superposition over all of the computational basis states of register X. But we're doing that for a reason. It's because it allows us to clearly see these controlled unitary gates. So why are they controlled unitary gates? Well, it's because the state of the qubits in register X impact whether or not this unitary operator is applied to register Y. So how does that work? Well, if we look at those exponents of U, we can see that those bits are appearing in those exponents. So if those bits are equal to 0, that means the unitary operator is not going to be applied. It's going to be deactivated. But if those bits are equal to 1, then we will activate the unitary operator. So it will act on that eigenstate. And you can also see other terms are appearing in these exponents. So we have powers of 2. We have 2 to the 0, 2 to the 1, and we go all the way up to 2 to the mu minus 1. And you can see that the power of 2 actually matches this subscript of G. So all of this notation is designed to be convenient so that the powers of 2 actually match. And we can actually use exponential laws to combine all of these mu terms over here. And if we combine all of those mu terms, we can turn this multiplication into addition within the exponent. And that's actually what happens in the next line. So you can see we have u to the power of g. G can be expressed in this binary notation as this string of bits, and each of those bits are getting multiplied by a power of 2. So if we use exponential laws, we can group all of those terms into a single term. We have u to the power of a sum of all of these exponents. And that sum is actually the definition of g. So g can also be written in this condensed form. So you can see that this second line over here is far more condensed. We're using a single index that goes from 0 up to 2 to the mu minus 1. And an alternative way of expressing that is by introducing all of these bits. But just know that these are actually equivalent to each other. And what is really important about these two expressions is that it shows us that applying this sequence of controlled unitary gates is equivalent to this expression, where we just have u to the g. So why is this important? Well, it's because the label for this state is the same as this exponent up here. And that's going to be very important. That's what we're doing when we're applying these controlled unitary gates. So now, what is the effect of applying u to the power of g to one of its eigenstates? So lambda is an eigenstate of u. So if we apply this operator to its eigenstate, we're going to get the eigenvalue. And because we're applying this operator, this unitary operator, g times, we're going to get this eigenvalue raised to the power of g. And if we have this eigenvalue raised to the power of g, we can actually pull in this g into the exponent. And so we're going to get e to the 2 pi I g phi. And that is going to be the coefficient over here. So now this g is appearing in the complex exponential. So remember that by definition, this is the eigenvalue of this eigenstate. So the eigenstate, lambda, is associated with this specific eigenvalue that is defined by the phase phi. And these guys are all the eigenstates and eigenvalues of the target unitary operator. It is the target of our phase estimation algorithm. So now we have this format over here. And the left-hand side of this expression looks very familiar to the quantum Fourier transform. And in fact, it is, by definition, the quantum Fourier transform. It's analogous to the discrete Fourier transform. And so we can write this in a condensed notation. We can use f subscript 2 to the mu to denote the quantum Fourier transform. And it's acting on this state with a capital phi. Where is this capital phi coming from? Well, in this purple box, you can see how lowercase phi and uppercase phi are related. It's a factor of 2 to the minus mu over here. And this expression can also be seen over here. This is another form where we just multiply everything by 2 to the power of mu. So if you multiply this top expression by 2 to the power of mu, this 2 to the minus mu is going to cancel. And you can see that lowercase phi is less than 1. It is 0 point times all this bit string over here. So all of these bits, they actually represent parts of a fraction. We're representing a fraction over here. And this notation is explicitly shown in this summation over here. So phi sub minus j multiplies 2 to the minus j. That is the general format of all of the terms in this expression. And j goes from 1 to mu. So we have mu terms in total. And then if we multiply by 2 to the power of mu, then we will shift this across the point, and this is just going to turn into a positive integer. We're going to have a string of bits. So all of these values can either be 0 or 1, and that is going to give us capital phi. So this is how you go from capital phi to lowercase phi. And you see, if you substitute this definition over here into this quantum Fourier transform, what you will get is 2 pi I g times capital phi and then 2 to the minus mu. And that's the definition of the quantum Fourier transform that we saw. It's analogous to the discrete Fourier transform. And you can see that throughout this entire process, this eigenstate of the unitary operator lambda, it has remained unchanged. It has been initialized and it has remained unchanged throughout this entire procedure. Now, why is that the case? Well, it's because the only thing that we did to it is apply the unitary operator u. And this unitary operator u is not going to change it, except by multiplying it by an eigenvalue. So we will get factors of those eigenvalues occurring, but the state is going to remain the same. And we can move those factors of eigenvalues up over here on the left, and we can regroup that and rewrite that as the quantum Fourier transform acting on this state. So this is the red snapshot. That's after we apply the sequence of controlled unitary gates. And we have seen why this sequence of controlled unitary gates is equivalent to this condensed form, where we just have u to the power of g. Now, let's have a look at the purple snapshot. The purple snapshot shows us the quantum state after we apply the inverse qubit, the mu qubit inverse quantum Fourier transform to register x. So we're not going to do anything else to register y, but we will apply the mu qubit inverse quantum Fourier transform to register x. And that is denoted with this symbol over here, where we have f sub 2 to the mu, and then we have an Hermitian adjoint. So this Hermitian adjoint tells us that we're applying the inverse quantum Fourier transform. And specifically, it is a mu qubit inverse quantum Fourier transform. That is what this subscript is telling us. So if we already have the quantum Fourier transform in this state, and then we apply the inverse quantum Fourier transform to register x, that's just going to undo the quantum Fourier transform. So this will just give us the identity operator acting on register x. And then we're just left with this state. So the state of register x is denoted by big phi, and the state of register y is denoted by lambda. And we can write this out more explicitly. Here we have what this big phi is actually telling us. What we have are mu qubit states. So we can see phi sub minus 1 all the way up to phi sub minus mu. And now if we measure all of those qubits in register x, we will actually get phi sub minus 1, phi sub minus 2, and then all the way up to phi sub minus mu. And that will give us the mu bit representation of phi. And because we're dealing with the exact case in this video, we're actually going to get the exact value of phi. But in general, when we generalize in later videos, we're just going to get an approximation. And that approximation is going to be valid up to around mu bits. It depends on some conditions which we will explore in later videos. But in general, this is a phase estimation procedure. So we're going to get an approximate value for phi. We're not going to get an exact value for phi. But in this special case, where phi can exactly be expressed in terms of mu bits using this notation, we can read off each of those bits. And then we can interpret those bits that we measure as this phi. So that is how we actually measure the phi value over here. And if we know what phi is, then we know what the eigenvalue is. So we have successfully determined the eigenvalue associated with this eigenstate of the target unitary operator u. So pay particular attention to this notation that was introduced in this video, because it will come up in the next video where we also talk about the quantum Fourier transform, and also in later videos where we see how to adapt the quantum phase estimation algorithm to perform the order finding subroutine of Shor's factoring algorithm. You can download all of the diagrams used in this video if you have a look at the description.